We're rolling.
Good evening, ladies and gentlemen. This evening we will hear a talk from Professor W.J. Bill Llope from Wayne State University. He is an associate professor in the physics and astronomy department. His research concentrates on the experimental study of the quark-gluon plasma and dynamics of relativistic heavy ion collisions, and the design and fabrication of large detector systems to measure these collisions. He has no significant expertise in astrophysics or gravitational theory, the physical foundation of this talk, but was drawn to a number of fascinating and historical and experimental details while reading a paper that, if you go back to the email announcement you received, you can click on that and go to that paper. So without further ado, I give you this final presentation of our general relativity concentration for this evening.
Good evening. Thanks, Jonathan, for that introduction. I'm very happy to be here. This is the first time I've been at Cranbrook. I know all the ways to not get to this building now. So that's good. I got that all settled. As the introduction said, and talking about an experiment that was done 100 years and a few months ago that really was quite simple. You basically have to go somewhere on the planet and take some pictures at exactly the right time. But those pictures have to be very precise, and there has to be a lot of luck involved as well. And this scene here is one of these photographs. It's a glass plate. It's this big. This is the goal of this experiment, is to collect these things. And I'm just gonna, I read the paper here, I read a few other papers, and learned some fascinating things about this experiment, which I thought would be fun to share. But as Jonathan said, this is not what I do. I'm not an expert on this topic. I am probably the least expert of anyone in this room on this topic. And what I do actually is study the state of matter called the quark-gluon plasma, which was the state of the universe, the whole universe, a few microseconds after the Big Bang. And we can produce that state over and over and over again in the laboratory by colliding nuclei, which you see here colliding. We collide these nuclei very close to the speed of light. And so they're carrying a huge amount of kinetic energy. And they collide, and a lot of that kinetic energy, almost all of that kinetic energy is converted into particle production. It's like somehow there's a relationship between energy and mass. And you might know what that relationship is, but if you don't, you will by the end of this talk. Right about now, in this collision, all of the protons and neutrons that we started with have been dissolved into their constituent quarks and gluons. And it's really a plasma, a fire of quarks and gluons, just like the fire you use to cook hamburgers and burn rainforests is a plasma. That's an atomic plasma, and the plasma that we're making and trying to understand is a nuclear plasma. So, as Jonathan said, I build detectors. We surround these collisions with these very large detector systems, bigger than this room, and we try to understand the physics of this collision by measuring all the particles that come out. I'm just trying to make it clear that I know nothing about astronomy, and here I am speaking to astronomers. So there's a special fear, a special kind of dread that is going through my head right now. But let's see how we do. Okay, so as you saw, basically I was sitting in my chair and I just was goofing around on the internet on my iPad like people do, and I ran across this paper and I started reading it. And the cool thing is it's so readable. It's such a readable paper. And it's full of all kinds of fascinating aspects about how they were able to do what they were able to do. And just within 45 minutes after starting to read this paper, I knew that there was a little bit of a talk here. But for a lot of the details, this paper is still available. You can click on it right now. And as I said, it's very readable, it's very tractable paper. Okay, so let's start with the sort of freshman physics stuff here, which was first laid out by Newton 300 years ago, 400 years ago, in a book called Principia. There's an island that this exploration is going to go to called Principe. I wonder if they chose that island as a reference to this book. He described the force that acts between two masses as a result of the fact that they have mass, and that force is called gravity, and the gravity acts along the line that joins them. And the amount of the force, the magnitude of the force, is given by a constant times the mass is divided by the radius. And this was fantastically successful in describing the motions of the planets. Where moons will be predicting upcoming eclipses. This basic mathematics that was laid out by Newton was really pretty successful for several hundred years. And then people started to notice something was going on with Mercury's orbit. And they thought maybe that there was a planet that they weren't seeing, because what was happening is that the orbit of Mercury was precessing, as if there was, which cannot happen if this is the only physics that's involved. You can't have a precession. For the physicists, a central force can never cause a torque. So this was a problem, and people thought that there was an unseen planet there that was causing this. Does anyone know the name of that planet that they thought?
Vulcan.
Vulcan.
Diana is an expert.
Oh, wow. Okay. I'll stop talking about that then. So we'll come back to this, because that was also a problem. Now, I'm going to recast this a little bit. I'm going to write this equation in the form of Newton's second law, which is that you just write the force as the mass times the acceleration, where the acceleration is given by this part. So this, you put these two equations together, you just get this. The point being that if you have a small object that is feeling the gravity from a much, much larger object, the acceleration of the small object as a result of that gravity does not depend on the mass of the small object. This is the acceleration of the little mass m caused by this big mass, and it does not depend on this mass here. So this is gravity as we know it. You can put numbers in here for the mass of the Earth and the radius of the Earth, and you get an acceleration around 9.8 meters per second. We've now mapped this. In Detroit, it's 9.81995 meters per second. Map the whole globe. In fact, we mapped the gravity on the globe with satellites, which is just too cool. But anyway, I think we all know more or less what gravity means. You know, it makes people fall. And poor Cary Grant. But the point being, the point I'm trying to make with this slide is that the acceleration of an object due to the gravity from something much larger does not depend on the mass of that little thing. So, and there's a famous experiment that's attributed to Galileo on the Leaning Tower of Pisa. It's almost certainly apocryphal, but it's a cool story, and apparently he drops two objects with different masses, and this one is also larger, and the drag goes like the size. So we're going to assume that this is, just view this as a small heavy thing, and this is a small light thing. And here he's showing in his experiment, by dropping these two things, that the acceleration of these objects in the gravitational field of the Earth is the same. That the acceleration of the objects does not depend on the mass of the object being accelerated. Now, you could do a simple thought experiment to show that this must be the case. And so let's say our hypothesis is that the heavier object will fall faster or hit the ground earlier than the lighter object. That's a hypothesis you can make. And if that's the case, here's the heavy one. This is the heavy guy. It's full, it's heavy. And we've dropped them here. Galileo has dropped them, and some short time later, the heavy one has fallen more than the lighter one. That's our hypothesis. But let's follow that hypothesis to its logical conclusion and see if it makes sense. So let's join these two masses with a very light string. Now, because they're joined, the lighter mass has to fall farther in the same amount of time because it's getting pulled by the heavier mass, which is falling faster. And likewise, the heavier mass can't fall as far as it would have if it was untethered because this guy is falling slower. It's causing some kind of drag. So this is the natural result of this hypothesis. But now if I use the same string in the two masses and I tie them together very tightly, now I have one object with a mass that's greater than this one and this one. The mass of this is in fact the sum of these. And so that, according to your worldview, must fall faster than this. So which is it? Is it faster or slower? And obviously, it can't be both. So it's a contradiction. And in fact, in all cases, they fall at the same rate, because it doesn't depend on the mass of the thing that's falling. And this can be tested. In fact, it was tested on the moon by dropping a hammer and feather. And I'm going to show you a video here, and I'm really praying that the audio works. I'll start the video in a second. This is from the 9th Apollo mission. Apollo, what does that say, 15? The fourth to land on the moon. And you'll be hearing from Commander David Scott, who will be doing this exact test in space. Now, I want to warn you that I have edited this video for comedic effect. See if you can figure out where that happens. Do you have to do something for sound to work? You think it's okay? Okay.
Can we copy the boat solar wind and Penetrator drum in the ETD?
Houston is telling him he's got to go do something scientific, and he's like, no, I want to do this.
A good picture there. Beautiful picture there.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that?
I love this joke. I love it so much. It's my favorite joke. That's Apollo 13, of course. And I think people in the Houston control room expected the hammer and the feather to land at the same time. So that was the joke. Okay. So it's true then that the acceleration of an object in a gravitational field or something else doesn't depend on that mass of that little thing, just according to this. There's no little m in this equation. So here we come to the 1900s, 230 some years after Newton's book, and we still really don't know what light is. We don't know if it feels gravity. We don't know if it follows Newton's laws. There's three possibilities. If you're talking about how light acts in a gravitational field, this part of this first statement is absolutely true. Light has no mass. So it should not feel Newtonian gravity at all, because the force on an object depends on its mass. So that's one option. The other option is, yeah, but light has energy, and energy and mass are related. There's an equation that I hinted at a few minutes ago that we'll come to again, that E equals mc squared. So maybe if something has energy, it has a kind of effective mass, and thus maybe it should follow Newtonian gravity. This second possibility is even though that this quantity here is zero, just assume light follows the Newtonian acceleration. That's the second possibility. And the third possibility is something else entirely. So we're going to try to see light feeling gravity. How do we do that? So basically, as light is traveling along a straight line, and it's coming past some heavy object here, as the object moves to the right, this acceleration due to gravity increases, and it's always along the line joining the center. And at this point where it's at its closest distance to the mass, this acceleration is the largest. And as this thing then moves off to the right, these vectors now point to the left and get smaller and smaller. The end result of this entire path is a kick to the right, a kick down in this view. The component of gravity perpendicular to the path of the photon grows in strength as it gets near the mass and decreases, it moves away. So the photon should bend a little bit down like this because of this acceleration. Okay, that's what Newton would say would happen if this was a little mass, a little golf ball. Right? So here's the path of something getting bent by this mass, and that means that when we're looking at the light coming from a given star, if its track has been bent, we see the star as being out here, but it's not there. It's here. So this is the difference between these two paths, between this thing being bent along this line and the star apparently being along that line of sight. And when the mass is not there and the star is along this line of sight, this is a measurable deflection. It can be a measurable deflection. And I've hugely exaggerated it in this picture, but this is potentially measurable. And if you're trying to decide if light deflects a little, or light deflects more, or light doesn't deflect at all, this is what you're trying to measure, is exactly this. You got to get the light going past something heavy, and then compare where the stars were when there's nothing heavy there. This is the very basic idea of this approach. So now we're going to rotate that view. In the previous slide, I was looking at the side view. Now we're going to put ourselves here. We're going to look in that direction. And here's a star field. And there's no heavy mass there that could possibly be bending starlight. And then we plop in a mass, and you see a couple things. You notice that all of the objects moved, but some moved a lot more than others. That's one thing you notice, is that the amount of deflection wasn't the same in all these cases. But the other thing to mention is that the directions in which these deflections are occurring are like this. They're all radial. All these deflections have to be radial. And the largest deflection is when the photon passes closest to your big heavy thing that you're using to see if the photon feels gravity or not. Right? So this is the expectation in this picture, which is entirely Newtonian at the moment. And so people tried this, and it turns out that things like whatever this is, Jupiter. See, I know a little astronomy. This planet here is way, way, way too light to cause any kind of deflection that we could possibly measure. So we want to use something heavier, something in our solar system that's way heavier, which is
The sun.
the sun. Right? So we'll use the sun. And so all we have to do is take a picture of a star field when there's no sun, and record all these relative positions of all these little dots of light. And then we turn on the sun, and so let's do that. Obviously impossible to see any stars. So, okay, we have a problem. We want the sun there, but we don't want to see the light from the sun. So we have to wait for a very specific thing, an eclipse. We'll use the moon to shut off the light. We'll wait till the moon gets in front of the sun. As I understand it, it's a complete accident that the moon so nicely blocks out the whole sun. And after some time, that's not going to be the case anymore, because the moon's moving away from us, and that's a shame. If humans are on this earth in many, many years, they won't have eclipses anymore. But okay, we have eclipses, so we can do physics with it. And so we'll use the moon to block out the sun, at least on a little point of the earth, and that's the point we'll go. And we'll try to see if we can see that light from stars that are close to the sun have been bent. That's the idea. So the expedition that is the subject of this talk had its eclipse on May 29, 1919. But that expedition was certainly not the first attempt to make this measurement. There was an attempt 7 years earlier in Spain. There was one a few years after that in Crimea. The poor graduate students on that experiment had a very, very bad time because they were all thrown in a Russian jail. I'll come to that. It's just kind of funny. I send my students out to do experiments all the time. I generally don't expect them to get arrested by another country and thrown in jail and all of my equipment to get stolen, but that's pretty much what happened here. They tried to make this measurement in Crimea, and unfortunately a war broke out, and we'll come to that later. They wanted to do it in Oregon a little bit later, but they still didn't have their instruments, and it's kind of funny that they were writing papers about the fact that we can't get our instruments back. They weren't writing papers about the science, they were writing papers complaining about politics. And reading papers from 100 years ago is, I have to admit, it's fascinating. It's totally unlike papers that scientists write today, which is all sort of clinical and dry. Back then, they had all kinds of personal details and the names and how things happened. It's really fun. So the problem is, among other things, that a lot of things have to fall in place for this to work. You've got to have good weather. You've got to have a good enough experiment, because as I'll tell you in a second, these deflections are very, very small. You also have to have enough stars. I'll tell you about that too. So these experiments are really quite hard. Okay, so let's put some numbers on this. And I did this on my recliner, just noodling on my iPad. I just did sort of a physics 1 or physics 2 type calculation of, I do an integral of the total deflection. I integrate over the deflection as a function of z. You end up with this integral, which at this point, scientists just look up. And it gives this answer. And so you can derive from purely Newtonian arguments that the amount of deflection for a light ray that passes at the sun's limb, it's called, which is at a radius r equal to the radius of the sun, 0.875 arc seconds. That's a very, very small angle. Okay, so, and I'll tell you how big that angle is in a second, but this is the Newtonian prediction, and it's very easy to derive. And so that's what we have. And then there was this guy. This guy. Physicists always, whenever they start learning about this guy, they always feel a lot smaller. He was young and a not so especially bright guy, apparently, with a low-stress job. He was sitting in a patent office, sitting around doing not all that much. And he had time to read the literature, and that's always the best thing to do, and he was doing it. And he also had the time to think through ideas. And in one year, in this year, 1905, the miracle year, he wrote 4 papers. This is a guy who's not working at a university. He's not in the club. He wrote these 4 papers here, which totally blew the doors off that club. One was about the photoelectric effect. This is the one he actually got the Nobel Prize for. One was about what we refer to as Brownian motion. On the electrodynamics of moving bodies, this is the deal. This is special relativity. I'll tell you what that means in a second. And does the inertia of a body depend on its energy content? Inertia is how Einstein said mass. So is energy and mass related? And in fact, he found that it was. And this was a huge result. These 4 papers coming out in this 1 year from someone that no one really had heard of was transformative, let's say. And up to that time, especially with the special relativity part, people had been perfectly happy with the way physics had been working before, because it works perfectly well for everything that we do as big humans on Earth doing our human things. You can have Tom standing here on a train, the train's not moving. This guy will see that Tom's not moving. So this is an example of two what physicists call reference frames. And so it's basically, there's one coordinate system here that Tom is living in, and there's another coordinate system here that, I don't know, Jerry is living in. If, however, Tom is walking and the train is at rest, this other guy will see that Tom is moving at 1 meters per second. Likewise, if Tom is not moving but the train is, this person will observe the same thing. And if Tom is walking and the train is moving, so everything is very sort of additive and comfortable, and velocities are additive. There is one absolute time that both Tom and Jerry measured. And, you know, that works perfectly well for almost everything, except that it's not true. It's not generally correct. This whole picture breaks down completely when this train is going very fast. And all of these equations go completely wrong when the train is going near the speed of light. They're just wrong. And there is no absolute time anymore. And that's a very hard thing to convince a physicist of when he's been doing this his whole life and it always worked. You have this young guy saying, no, it's not the way it works. So this was special relativity fixing this. I'm not going to go through how these equations change for special relativity. They're quite different. But this is called special because it's only for the case of non-accelerating frames. The train is not speeding up. It's not accelerating. It's only going at a constant speed or it's at rest. And it can't rotate. No rotating trains. This is called special relativity as it is just a special case of the full theory. And this special case is ignoring gravity. So this theory is not yet general. And I think you probably already can guess what the next kind of relativity is that will solve this problem, but we'll get to it in a second. So Einstein was basking off of all this fame because of his papers in 1905. And he was really troubled because he thought, and this sounds arrogant, but it's just Einstein being matter of fact. All of the natural phenomena, all of them, can be discussed in terms of special relativity except gravity. Einstein's saying special relativity solves every problem except one. But he was not happy, even though he solved 100,000 problems minus one. He's upset about that one thing that doesn't fit in his theory. He feels like he can fix this. It was most unsatisfactory to Einstein that although the relationship between inertia and energy is so beautifully derived, E equals mc squared, in special relativity, there is no relationship between inertia, again mass, and weight. So what is the relationship between inertia and weight? Now, Newton had equations for this, but it's pretty empirical. It's not a real general underlying theory. So the trick, he said that he was sitting in the chair in the patent office when all of a sudden a thought occurred to him, if a person falls freely, he will not feel his own weight. And if you just think about that for a second, if you're out in the middle of space, out in the middle of deep space, you're separated from all possible other planets, you won't feel any gravity and you'll just feel weightless and you can move your arms and legs around and that'll be that. But the same is true if you're falling in a gravitational field. If you're falling in a gravitational field, and you can't feel the wind rushing past your face, it's exactly the same thing. You have no resistance to movement. It's exactly the same. And that correspondence between there not being gravity and someone falling in gravity being the same was what pushed him, he said, to that theory. And there's the thought again. So basically, falling feels exactly the same as being in gravity. And likewise, if you are, say, in a box, in a closed box with no windows, and that box is right there on the floor, on the surface of the earth, I could drop a ball in the box and I would feel the ball go down, and so I would know there was gravity there. But the other thing is my box could, instead of being on the floor, it could be attached to a rocket. And that rocket could be accelerating with the same acceleration as gravity is providing. I would drop the ball in my box again, and it would fall. There's no way I would be able to know the difference between a box sitting on the surface of a large planet or this box being accelerated by a rocket. We assume the complete physical equivalence of a gravitational field, this guy, and the corresponding acceleration of the reference system, this guy. They're completely equivalent. But then Einstein really had to learn some math, because the trees he was barking up needed math that he did not have. And that's why it took like over a decade for him to go from the special relativity to the general theory. Because he had to learn a lot about non-Euclidean geometry, Riemann spaces. This is serious math. And so he had to learn that. But once he did, he was able to use it to great effect. And the result is the following. This is, it's called G mu nu. It's a tensor. It's basically a matrix, right? Rows and columns. And here's T mu nu. And I'll tell you what these are in a second. But they're related by constants. That's 8. That's the relationship between the circumference and the diameter of a circle. That's pi. That's the gravitational constant again. It's just a number. C to the 4th is also just a number. So this is a constant. So we have this tensor and this tensor that are related by a constant. And I want you to recall that we have this quantity energy and this quantity mass, which are also related by a constant. And the reason I'm showing you these two is to make a very simple point. It was a very hard thing for physicists to accept that energy and mass were really the same thing, just related by a constant. Energy and mass are the same thing. You can convert energy to mass and mass to energy. It's not a problem. Energy and mass are the same thing. It's like saying kilometers and miles are the same thing. When I say equals mc squared and I say energy and mass are the same thing, I mean it in the sense that kilometers and miles are the same thing. They both measure a quantity called distance, and there's a conversion factor in between, but they're fundamentally the same thing. So energy and mass are the same, really the same thing, and this was a revolutionary idea. It's totally true. But this field equation he's come up with is saying the same thing. This G mu nu is the, let's get ready to sound impressive, the geometry of a fourfold pseudo-Riemannian manifold representing space-time. I'll show you what that is in a second. Don't worry. You know what space-time is. This thing is just a number, and this thing is called the energy and momentum tensor. This is the distribution of energy and mass. So somehow, space and mass are just as much the same thing as suggested between energy and mass in this equation. And this is really, this was, if you thought the stuff he did in 1905 was hard for the field to understand, then he gets into this.
Oh, God.
So basically, the way to picture this is that when you have a big heavy thing like the Earth here, it is, now this is an analogy that you'll often hear, but don't push this analogy too far because it doesn't work. Think of a ball in the middle of an elastic sheet of, I don't know, spandex or something. And basically, if you're holding that elastic sheet horizontally, the weight of the ball will make a kind of a pit there, right? And so if something came by like this, it would curve, but it's only curving because space is curved. It's still going in a straight line, but space is curved. It's a completely different view of what gravity does than Newton. Newton had this equation to tell you how much the mass was. But what Einstein is saying, yeah, that's fine. That's what happens if the masses, aren't too big, and that's a case that works often for humans. But what Einstein was saying that this is a much better picture. So and likewise, the space-time curved around this mass, but likewise the mass is there because that's where space-time is curved. These two things, the distribution of mass in the universe and the curvature of space-time, are the same thing up to a constant. which is wild. It's just wild. And when physicists like me learn about stuff like this and they ponder the kind of brain needed to figure that out, that's when physicists like me wonder how they're still getting paid. It's a level of mental acuity that is, I'm not there. And I don't believe I ever will. Okay, so, you know, this is kind of cool. People in NASA can use this to make rockets and things move. Here we have a flyby of Neptune by Voyager 2, and you see that Houston has used where the planets are to send the rocket past some other planet, and then this is because this planet has curved space-time. This rocket is going in a straight line in the rocket's view. They're not using any rockets or thrust or anything to make this curve. It's just that space is curved and the rocket's going in a straight line, so it curves around. And that's how they were able to do this flyby of Neptune. It's a much better picture, it's much cooler. What they did for Galileo, and I'm going to let this image reset. Because what they do in this is we launch from this green one, that's Earth. And they, come on, reset already. Just wait a second. There we go. So they're gonna, Galileo's gonna rattle around in here in these inner planets, and then they just loft it off into space and swish. There, right there. It's fallen into the gravitational well of Jupiter. It's really quite cool how they can move rockets without using any fuel, just by using the curvature of space-time. You can calculate all of this with Newton's equations too. You didn't need general relativity to do this in this particular case. But I just find this picture very easy to visualize. So general relativity also makes a specific prediction for the deflection of light that accounts for special relativity too, and evaluated at a distance of closest approach equal to the radius of the sun, you get 1.75. This, just a kind of funny way, is exactly twice the Newtonian prediction, which was 0.875 arc seconds. So Newton's prediction here is twice. Now this angle is very small, so all the way around, you turn in a circle, that's 360 degrees. You divide that into 360 little segments, so you have 1 degree. You divide that by a factor of 60, and that is then an angle measured in arc minutes. And if you divide it by 60 again, that's an angle measured in arc seconds. So if you go outside, and I don't know if the sun's out, you guys know, sorry, the moon. I know the sun's not out. I don't know if the moon's out tonight, but if you go out and look at the moon, then looking across the diameter of the moon, that's about half a degree, or 31 arc minutes, or 1860 arc seconds. So your index finger at arm's length is about 1 degree of arc. The deflections that we're talking about here are about an arc second, which is if you took a quarter and you viewed it 3 and change miles away. That's a small angle, and that makes these experiments hard. And that's why we need the sun also. So not a trivial experiment. It sounds easy, just go there and take a picture, but you're trying to take a picture that will look very much the same because the effect is so small. All right, so here we are. Some things in the Balkans are not going well, and the politicians didn't handle it well. They're sending letters to each other, and they're basically giving the shrug emoji, go talk to somebody else, I don't care, and war breaks out, and 70 million military personnel, every major European nation is involved. France, Russia, and Britain are on one side, and Germany, Austria, Hungary, and Italy are on the other. And it's a everybody's involved. in general, though, when you're doing an experiment, you need two kinds of physicists. You need the theorists and you need the experimentalists. And these two groups work and feed and help each other. It's a symbiotic relationship. And in this case, the theorist, and there was exactly one theorist, maybe two, was a German. And all the experimentalists in this case were all British. And so basically the two sides of your experiment that you need to work together are on opposite sides of a world war, and there is no internet. There's no cell phones. There's none of that. So, you know, how information moves in this situation is not at all like we deal with today in this information age. Willem de Sitter, whose name is actually coming up in modern physics also, basically squirreled away a copy of Einstein's paper and handed it to Eddington. And Eddington is one of the experimentalists that we'll come to in a second. So I just thought that was neat. So here's the timeline. 1801, this guy named Solder publishes the result that I did on my recliner. Right? 0.875 arc seconds of deflection at the sun's line. 1905 comes and goes, and special relativity is presented. 1908, Albert, this is after 1907 when he says that he's really upset that he can't solve gravity. He starts working on the light deflection in a gravitational field, and then he sods off someplace else. He returns to the problem a few years later, but gets the same value as Solder did. He gets exactly the same result, which is wrong. Einstein was wrong. In 1912, we had this first attempt to measure the deflection, and fortunately for Einstein, the experiment failed due to bad weather. In this era, people are thinking about what else to do. Can we do this during the daytime? It's just too hard to see stars during the day, but they were thinking about ways they could beat that. Maybe you could use planets instead. None of that worked. So this is when they go to Crimea, they try to do that. Then the war breaks out, all the graduate students get arrested, all the equipment gets, impounded, which is a problem. And then finally, 5 years after Einstein got the wrong result, then he publishes the correct result. And Einstein is actually quite lucky that these experiments did not work. Because if they did, then Einstein now has a reputation for publishing things that are wrong. And I don't think anybody in this room thinks of Einstein like that. Everything that Einstein wrote in 1905, we test every single day. I test it for a living. I basically use special relativity as my job. And it's right. Everything Einstein's ever said has been right. And for 5 years, had either of these experiments had worked, Einstein would have been wrong. Now, obviously, when the full theory came out, he would have rescued his reputation. But I just thought it was interesting that for a brief period, Einstein was just way wrong. This theory also solves this Vulcan issue and correctly describes the precession of the perihelion of Mercury. And here's where we get our result from general relativity, which is exactly a factor of 2 larger than the Newtonian result. November 11th, 1918, the war ends, and it's only about 7 months until this eclipse that's coming up. And so one of the most fascinating things in this paper is all of the scrambling these guys had to do, because all of their technicians, everybody that worked at their university, was doing things for the war. You know, if they needed equipment built, the technicians were involved in the war effort. The scientists had nothing. So in this last few months, they were really scrambling. Okay, so I'm not sure how I'm doing on time.
15 minutes.
15. Okay, I better hoof it a little bit here. These are our 3 options. It was Frank Dyson, the director of the Royal Greenwich Observatory, that said that this eclipse right here, May 29th, 1919, was going to be a really, really good one. Because it's going to be in front of the, I don't know how to pronounce that. Hyades? Just Hyades? Okay, I'll let you guys say it. It's a very dense star field. And you need a lot of data points for this to work, for reasons I'll tell you in a second. not all of these stars are actually in one constellation. There's some in a constellation that's way behind this guy. But this star field presents many dots of light that if we can get an eclipse in the middle of this star field, then we have the possibility of measuring this deflection. This, of course, is the head of Taurus the Bull. If you're ever looking for this, I'm telling the wrong group of people how to find this, so there's Orion's belt, and if you follow that, you'll see the head of the bull. So this is their star field that they're going to use. Here's the nautical almanac for that year, which shows the shadow where the sunlight will be perfectly blocked by the moon, which proceeds from, so I've added these red lines to make it a little easier to see, but this is South America, this is Brazil, there's a big stretch of Atlantic Ocean, and over here is this little island called Principe. So this is a little bit of a timeline. They considered, Dyson draws the attention to this eclipse in front of that, the bull. They considered a number of sites. Cape Palmas they rejected because they were worried about the weather, but they shouldn't have been because on that day the weather was great. Lake Tanganyika in Africa, at the very end of the eclipse track, they were worried that the eclipse would be too low in the sky and there'd be a lot of atmosphere for the light to go through, which would cause refraction. And they also considered this site in Brazil that was suggested by a colleague. They set up a commission and they asked for funding. They asked for £100 for instruments and £1,000 for the whole thing, which is chump change. It's nothing. The cost of living is about a factor of 50. The value, however you phrase this. So in modern language, that's $5,000 for the instruments and $50,000 for the trip. Really quite cheap. They formed a committee. Then they had to choose the sites, and they picked Sobral in Brazil. It's right there. And this website, by the way, timeanddate.com, it's pretty cool. You can go and you can look, and there's animations of how this eclipse looked to people standing right there at that time. It's really pretty cool. So if you want to goof around with those animations, they're available on this site. I used this site to tell me exactly when things started and stopped, for reasons you'll see in a second. But they're going to send one team here. They're going to send the other team here. There's a series of islands, and Principe is one of them, and it's right there in the path of totality. Here's Tanganyika, where they rejected. And so those are the places they need to go. And Eddington, so I'll show you these people in a second, but Eddington is kind of the leader here. He's the young firebrand physicist. He'll take the team to Principe. Dyson, the royal astronomer, and Father Cordy. Father Cordy is the hero of this story, as I'll say in a second, and he got no credit for it in the paper, at least in terms of the authorship of that paper. I'll say what's going on there. And so they basically are trying very hard to get prepared, even though they have very little resources. So during one of these meetings, this father suggested that they also take the Royal Irish Academy's 4-inch telescope and 8-inch celestat, I think. I'll tell you what that is in a second. They're super cool. Bringing this telescope saved the mission. Bringing this telescope saved the day. But he was unable to go, unfortunately, and I think he really should have been an author on this paper. He wasn't. The other guy, I think, should have been an author on this paper, but wasn't. I have a guess why, because he screwed up. And this other guy, we'll get to him in a second. But this guy was really impressed with. He really saved the day. He's the hero of this story. So basically, let's zip through this. They had a lot to do, and by March 1st of 1919, they sent everything to Liverpool, which is there, and London is here. And basically, they're going to take boats, and they're going to go to these two places. And I had read this paper just a couple of months before this eclipse happened this year, and it was a couple of weeks later when I realized, wait. In a couple of weeks, it'll be the 100th anniversary of all this. So I started live, so here are the people. So there's Dyson we've met. Davison, sharp cookie. Eddington, very sharp cookie. This is the guy that screwed up. And he was not an author of the paper, but probably would have been. This is the only picture of Cottingham. He's basically a clockmaker. He made the seal stamps. So these are our players. But as I was saying, when I realized that we were coming up on the 100th anniversary of this, I started live tweeting the whole experiment. And so March 8th of this year was the 100th anniversary of when that boat left Liverpool with all their stuff. And then I just kept tweeting. They stopped in Lisbon to go see the observatory. They all signed the guest book. There's Eddington. There's Cromwell there. There's Cottingham. And we just, one team goes off. They get to Pará, Brazil. They stay there long enough to send a telegram. And then they go upriver to party for a couple weeks to relax, because they're there way early. The eclipse isn't for some months. Then they come back. Everybody's just down there in Brazil waiting. Then April 9th, the other team, who was in the Madeira archipelago, set sail for Principe on the steamship Portugal. I'm sorry, I couldn't find a picture of that boat. And here's the island. After some looking around, they pick a site up here, which is very well Eclipse plantation. And they wanted to be away from this region where there are mountains and thus clouds. So they pick this site, and then they start trying to get their stuff there. Finally, these guys are finally getting close to Sobral. And now the equipment, April 28th, 1919 arrives at Principe, where they actually had to carry it by hand. Both teams end up getting where they need to be on or about April 29th, and that's 1 month before the eclipse. So everything's looking good, and this is what they used. So this is the astrographic reflecting telescope from Greenwich. They obviously could not bring this whole thing. It's quite huge. But what they did was they took the main object glass out of this thing. That's the key part of this piece of equipment. And they basically just built steel tubes. And instead of, in this case, where they're letting the telescope point wherever the telescope needs to point, what they're going to do is a different thing. They're going to have the telescopes just laying on the ground, and then they're going to use a mirror to direct the light from the eclipse off the mirror into that telescope, which is just laying horizontally. And that mirror has to move with the rotation of the Earth to keep that image in one spot. And the device that tracks the rotation of the Earth to keep stars at one location in the telescope is a celestat. And it's basically a clock-like mechanism with a weight, and as the weight pulls down, it applies a force that can turn a gear, and it can keep that thing moving so that you keep the image right on your photographic plates. So here's what it looked like. This is the steel tube that they built, and this is the Irish Forage telescope. You notice that they put it on its side because some smart monkey said, well, if we put it on its side, we can get a few more stars. So they put it on its side. And here are the two celestats, so both of these guys are aiming somewhere up here, and the eclipse will be up there, but the eclipse will move across the sky a little bit during the couple of minutes. And the job of these two devices is to keep that light going directly down this tube so that they can expose these photographic plates. This is the actual experiment in Sobral. Right, so I've just described all that. So here we are. This is the day of the eclipse. And now, sorry, I should change that title. I gave this talk on the day of the eclipse at Hopcat, and I'm giving it, but I'm sorry I neglected to fix that. The eclipse will start about 9 a.m. in the morning Brazil time. They'll have about 5 minutes of totality. They'll take pictures in the middle half of that at Principe, which is at GMT. It'll be 2 o'clock in the afternoon. But as totality is coming up, what they do is they started a metronome, and reading the paper, you can really feel the excitement of when the eclipse was happening, and these guys are scurrying around trying to get all their equipment set up. So a metronome was started, and the time in seconds was called out because they're trying to expose these plates for very specific amounts of times. And the paper doesn't give too much detail about why they chose these. It has to do with the photographic plates they were using. It's all very technical, and I didn't try to learn too much about that. But they were very sort of military in the way that they organized this data collection, because they had only a couple of minutes, and they're trying to take as many good pictures as they can in those couple of minutes, and they really kind of planned this out. So that morning in Brazil, I tweeted at exactly the second that they started taking pictures, plus 100 years. And so I tweeted at whatever it was, 5 o'clock in the morning. And they start taking their pictures, and that's when it started. Oh, sorry, 8 o'clock in the morning our time. And I don't know what time Twitter was on there. A little 5 minutes later, they stopped, and at this point, where they had just finished the photography in Brazil, there were thunderstorms covering the island of Principe, which must have been making Eddington nuts. But they took a few pictures. When it was over, Eddington sent a telegram to his colleagues in London through cloud, hopeful. Here's a picture of one of these plates, taken at Sobral. You can see they got a pretty cool coronal mass ejection there. These are not all stars. Some of this is just damage, I presume. But this is basically that plate that was shown on my first slide. These deflections, I'm going to point out again, are very, very small. And this is the picture of a star. And that length of that arrow is about how much that guy is going to deflect. So the deflection of the star is a lot smaller than the size of the star on the picture. So it's not going to be easy to make this measurement. Even if all the photographs, even if the weather was perfect. So how do we make the measurement? So here's a picture of a glass plate, and here's all kinds of stars, and here's our eclipse. Basically, you take a set of pictures when the sun is not there, and you take a set of pictures when the sun is there, and you compare them, and you're looking for these radial deflections where the stars closest to the sun are deflecting more, and the stars far away from the sun are deflecting less. And they use this, device to try to make these measurements. They have to do some algebra here. The deflection in the x direction is given by this series of terms, and the deflection in the y direction is given by all this. The number they're trying to extract, so they're measuring this. They're measuring so many of these other things, and they're trying to extract these two things, Lx and Ly. There's a lot of things that can change, like where the plate is inside the telescope, and if it's curved, if it's tilted a little bit, if the check plate with respect to the axis of the telescope is not at the same angle as the plate taken when the sun is on the telescope. There's lots of shifts and inclinations that are not this kind of deflection that you need to correct for. But basically, you have two end equations for n stars. You solve these using least squares. This is straightforward stuff. But you need good data for at least 6 stars. So, November 6, 1919, 100 years from before 2 days from now, are when these results were announced. I'll show you the results in a second. They were announced at this place right here, London's Burlington House. And one of the things they talk about that's also in the paper is that one of these guys, who's not an author on the paper, and I think for this reason, he set the focus of this big, beautiful astrographic telescope the night before when it was cool, and then the sun came up, and it wasn't cool anymore, and metal expands, and the focus got all messed up. And so the data from the 13-inch telescope, the big thing that they had spent all this time and effort dragging all the way down across the whole Atlantic Ocean, they couldn't use any of that data. The 4-inch telescope from Father Cordy worked great, and they got lots of pictures there. Eddington, of course, over on the other side of the Atlantic, was looking through clouds. So that's what I mean when I said the 4-inch telescope saves the day. And this is a picture from that 4-inch telescope. Here you see it's tilted, and you see all the stars that they could find, and there's where the eclipse will be. They could get a couple plates from Principe. There was, I mean, all kinds of things are just coming and getting in their way. There was a steamship company strike. Eddington had to leave early, so he couldn't get check plates, so he had to rely on check plates taken in England months earlier. And there's going to be all kinds of criticism. There's going to be criticism from Cromwell blundering. There's going to be criticism for this. And there was the thought of, you know, maybe Eddington is too married to this, and he rejected data that didn't agree with his desired result. That was the criticism. It's not true, as you'll see. But there was a lot of talk about that. So here's the result. Finally, here's the result. This line is where the stars would be on these pictures if Newton was right. This line is twice that line, and that's Einstein's result. You know, there's no error bars here, so I take off a few points on your exam or on your lab paper if you didn't have uncertainties, but you can see that the data clearly favors Einstein's prediction. A couple of days later, I guess Sunday, our time, 100 years before that, on Sunday, the New York Times comes out with this headline, Men of science more or less agog over results of eclipse observations, Einstein theory triumphs. A book for 12 wise men, no more in all the world. So 12 people understand this, is what the New York Times is saying. The thing I thought was funny and cool is, stars are not where they seemed or were calculated to be. But don't worry, it's okay, don't worry. I just thought that was funny. There's something funny about that.
New York Times, yeah.
But that cracked me up. Don't worry, it's okay, it's okay, it's okay. So day after day, global media ran editorials and additional feed. I just have a couple more minutes, and this is actually the cool part of the story. I think is how Einstein dealt with this. He becomes an instant celebrity. At this meeting, J.J. Thomson, another very, very famous guy, he discovered the electron, which is pretty important. He called it one of the highest achievements of mankind. Let me just skip this one. It's basically Einstein throwing shade at Planck. Let's skip that one. So Abraham Peiss, in his excellent biography, this is the biography of Einstein. New York Times records no mention of Albert until November 9th, until this meeting, until this result. And then from then on, the entire rest of his life, not a year went by without a mention of his name. He's surprised and confused by this, and he's like miserable. And to understand why, I want to. This is the slide that I want you to understand. When you see pictures like this, you think of Einstein as this like kind of disheveled but kindly, friendly uncle, right? He's just, we know how smart he is, but look at him. He's like one of us, right? He rides a bike. He sticks his tongue out. You know, that's the picture. But I think there's a different picture of Einstein, which may explain why he's so miserable by this result. Picture instead of a 40-year-old who, when he steps into a room at a party, wherever, women start fainting. People wanted his opinion about even stupid things. And for years, if anyone said anything wise, eventually they were attributing it to him. So how would you feel if you're just a guy who figured something out and you're trying to go to a party and you walk in the room and everybody faints? It's got to be heavy. It's too much. And I can totally understand why he didn't like this, why he didn't want this popularity. For him, he was solving a problem just using his own brain. It made perfect sense to him. It's like us when we solve any problem we have. We figure it out, and he figured it out. Well, Einstein was surprised how impressed people were by that. And they remained impressed his entire life. So here's the experiment, just a couple more slides. Here's the experiment that we did. The uncertainties are huge. The Einstein prediction is this line here at 1. But you'll notice as time went on, we have other predictions. The light we're using to see this gravitational deflection does not have to be visible. The light that Eddington et al. Used was visible starlight, and they needed the eclipse to see it. But we have other ways of looking at light now. And they're, in fact, able to do hugely precise measurements of this deflection, where the uncertainties are now not 20% anymore, but more like 2 × 10⁻⁴. So this is what I mean when I say Einstein got the problem right.
Yeah.
He nails it. Okay? We use this fact. We actually do science because we know that light will deflect as a result of this. There's something that we call gravitational lensing. There's something very heavy here, and if you look at this, you can see structure in there, right? There's bright spots and dull spots in this kind of image that's surrounding this heavy thing. That is the image of galaxies that are behind this thing that we can see because the light came out and bent around and came to us. And we can, in fact, take data here. We could put our telescopes and point them here and measure things about this galaxy that we couldn't see unless light was deflected, according to how Einstein calculated it. This is our word of the day. This is called gravitational lensing. The story gets even better, and I know you all know about this. The first direct observation of gravitational waves, we're talking about space-time. I made the sheet analogy. Imagine waves on that sheet. And this was a prediction, more or less by Einstein, that this should happen. But much more recently, we built these huge interferometries. These are actually modern, much better Michelson-Morley interferometers, and they're monstrous. And they're able to measure the squeezing and stretching of space-time that is, about 1,000 times smaller than the size of a proton by using the interference of light from these lasers. And that's caused by two objects that are spinning together and merging. So we now are doing astronomy on space-time. This was the Nobel Prize in 2017. Kip Thorne, a very, very nice guy. I was very happy to meet him. He came and gave a colloquium at our department that Jerry organized. It's on my YouTube channel. If you want to go see this lecture, it's really great. He explains it very, very well. It's one of the best talks I've ever seen. He was also, the Interstellar movie with McConaughey was also his idea. He wrote all of that, so the treatment. Very nice guy. He also got in a famous argument with Hawking about the information paradox. But yeah, you can go see this video on my YouTube channel if you want. But this is a whole new era in astronomy, and these events were happening where these large mergers were happening, and space-time was getting struck was getting plucked like a guitar string. But now we're listening, and so we have a whole new age of astronomy that we can deal with. In fact, people can do this experiment. You guys can do this experiment yourself, and people do this. And in fact, they get results that are, I mean, look at this equipment. Well, Eddington would have given anything, probably 2 or 3 of his children, to have this kind of equipment. And you can measure these beautiful deflection curves here, which are, of course, exactly on top of Einstein's prediction. When's this going to happen again? This is the one that happened a few years ago. Here we have one that's going right pretty much through southwestern Michigan, but that's 100 years from now, so that's not going to work for me. However, there's one in about 5 years, April 8, 2024, which is going right through Cleveland or something. So, especially you guys, this is a perfect audience. You guys, if you're interested, try to see the stars close to the sun during that eclipse. Maybe even with your awesome equipment, you can measure it. Those stars are not where they seem, but don't worry. All right, here's one for you. In that web link there, I put like 8 or 10 papers, including the main one, and so some of these papers are much more recent, like from the 70s or 80s, and if you want more reading, they're sitting there for you, and there's my email address there if you want to chat.
So we are over on time, so I want one really good question.
I apologize for being over.
Go ahead.
Enthusiasm. How did Einstein's theory solve the Mercury precession?
I think you have to ask her.
How did
I have to ask the Vulcan expert. No, because it's natural in that theory. If you picture space-time as curved, then it's not a surprise that this orbit can precess. You can throw a ball into this analogy. So if you go to a children's museum, you'll often find this analogy set up where you can put a ball in the middle of an elastic string and then throw marbles across it. And it is possible to do that with a marble in which you get this precession. And so it literally is an aspect of that curvature. Like, I'm going to pretend like I can't give a more detailed answer because that's all manifold, tensor mathematics, and it'd be too complicated. The real answer is I don't know a better explanation. It is literally, though, from the fact that space-time is curved. It cannot come from Newton's law. There's no way that a central force can make that trajectory curve. So basically, and Newton knew this, and Tycho Brahe knew this, and Kepler knew this, that the Kepler's second law is basically a statement of the conservation of angular momentum. And that always happens when there's a central force. And central forces like gravity cannot exert torques. They just can't. And so there's no way, if you have an orbit that's going like this, as an ellipse, to make that orbit turn like Mercury's was. But if that orbit is in a place where space-time is conserved, space-time is curved, then it's perfectly easy. You can even do it in a children's demonstration.
Well, I was thrilled to see a presentation with an integral.